Okay, it's looking like we're live. All right, welcome everybody. I was thinking of doing a quick video, and I've just thrown this together. I was playing with it to try and do a demonstration a while ago, but I got a bit into the code, got it working, and then forgot all about it. So I've been prompted today to put together a very quick tutorial on how analog input pins on an Arduino can be used for multiple buttons. And let me just move my microphone out of the way. Okay, so what I've got in front of us is a Arduino Uno. Now I can't demonstrate to you with the simulator here how the HID joystick code would work, but this is essentially how you would take a rotary switch or a resistor ladder and turn it into a bunch of single multiplex buttons from a single analog pin. On the simulator, I've got a LCD panel. This is just basic LCD code, typically just copied from an example, and I just made my own, overlay here. So what I'm looking at here is analog A, and analog A0 and analog A1, and you'll be able to see here A0 and A1. These are the analog pins on an Uno board, and I have these coming out to two separate circuits here. And what I want to demonstrate is how the how the code can split these into two sets of buttons. And I want to show you that they're exactly the same, except one's a resistor ladder and the other one is a potentiometer. Okay, so these are just 10K pots, and these are all just multiplexed, sorry, not multiplexed, daisy chained 1K resistors. Okay, so in the circuit, let's see if I can zoom into the circuit a little bit for you. All right, we have a VCC up to the top button and a chain of resistors, and each one being 1K. And in here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 buttons that I'm looking to try and get out of this. I also have a pull down button for a pull down resistor. I can't remember why I put that there. Anyway, I'll take it out later and see what happens. Like I said, I did this a little while ago, but I've got a voltmeter, so you can actually see what is actually happening. Is actually happening to the analog pins on both versions of the circuit, and this is a standard potentiometer, 0 to 5 volts, and whatever the center tap or the swiper of the pot is actually going to be. Now, what I want to demonstrate as we simulate the circuit here is I've got two pieces of code, and they are slightly different because they're approaching the whole splitting up of the buttons and the 1024 steps the analog pin can read. So I'll just stick with this one here. I think this is A0. No, that's A1. Okay, we'll start with A1. Why not? So A1, you'll see on the screen, and on the left-hand side, I'm reading the actual value of the potentiometer. So that's 5 volts, and it 5 volts, and it reads 1023. So it's basically pulled up to VCC. But you can see the button, or the B, is equal to 10. And we've got button 9, button 8, button 7, and so on, all the way down to button 5. And you can notice when we get to button 5, we're at halfway. We're about half of our 1024, and you can also see we're also about half, just under half of our 5 volts VCC. So you can see how this is linearly proportional, and the buttons are split into 10 buttons. Now, how does the code work for this? So zooming over to here, we have a basic LCD setup. We set up 2 analog input pins. That's what I'm using. We start the LCD screen, set the cursor. Sorry, this is doing the analog A0, but this section here, this is analog A1. Okay, so all I'm doing is setting the cursor to the second line, printing A1 to the screen, and we're just doing an analog read of the A1. So this is just a basic, what's the decimal value of the analog pin, okay? But what this bit of code does is this goes and calls a separate function called analog button read, and I tell it the two things I provide is which analog pin you're going to read and how many buttons do I want to get out of that pin. The good thing about this piece of code is, and like the other one as well, is you can effectively use it this one piece of code for as many analog pins as you like. So let's scroll down to, what do we do? Analog button read. That's right, analog button read. So here's what we've got. We've got 10 buttons, okay, and you'll be able to see I marked up 1024, 930. Oh, that's right. I think I worked out what the outer thresholds were, which is why they're either side. Perfect. Okay. So what this piece of code does, can I zoom into that? Let's see if I can make this code bigger. Here we go. That's better. Okay, so I pass in the pin, which was A1. We want 10 inputs, and the first thing we do is say, right, we want to take the 1024 and we want to split it into 10 chunks. Okay, so when we go and take each of these resistors, very important, these resistors must be the same value, otherwise you won't get a linear stepped output. Makes sense, I suppose. And what this does is it reads the analog pin, puts it in here, and then it wants to check the range. It wants to read what the range is. So it takes 1023 and it divides it by the number of inputs. So that's 10 chunks of 102.3, and the range is going to be 102.3. So what this does is it says each one of these is going to be about 102 apart. Okay. So this is where it gets a bit tricky. I'm going to use an index counter. So I initialize it at 0. Okay, and I keep counting it so long as I'm counting up to the number of inputs I've asked for. And I go and say in this very long if statement here, let me pull this along, and I'll explain what this does. We have two sections. We have this section here, which I'll dub as being the lower threshold, and this as being the upper threshold. Right there. There's a lot of curly braces, or curly brackets. Now, how this works is the analog value that we've just read off the pin, is it equal or greater than the input, the 0, because we're starting off at 0. 0 times the range, which is just going to be 0, minus the range divided by a third. Now, what I'm doing there is I'm saying, look, at 0, is it plus or minus, and then plus or minus, sorry, this is going to be the minus. Here's the minus, a range, and this is the plus, the range. And what I'm doing is I'm creating a 30%, or give or take 33% buffer either side what the even split should be. So I'm creating an upper and a lower threshold. So if these are going to be 91, 174, 278, then I expect to have 30% lower, 30% higher, and that is going to be the window at which that will be button 1. Same thing if we went to 464, 30% lower and 30% higher, or it's not 30%, it's 30% the size of a block. Okay, so you'll never get a buffer that will a range that will overlap the next one. Okay, so that's what this code does. It basically says keep stepping through, and when you find what the analog pin is, and it keeps stepping through and it goes round and around and around, and each time this is incrementing by 1. Every time you increment by 1, it's 1 times the block size, 2 times the block size, 3 times it. So here is 0 times the block size, 1 block size, 2 block size, 3 block size, 4 block size, 5, 6, 7, 8, 9. Okay, and what it does is when it finds which one of these block ranges it fits in, it returns the value of I. And the idea is if you then just add this piece of code here into your joystick.set button, I think it is, and then call this, the I value will come back and it will be button 1, 2, 3, 4, 5, 6, or 0. You know, it'll go all the way up to the number of buttons you wanted, or it will default to 0. And yeah, so I use this piece of code to directly set the button, and then I let the analog input pin determine through this little algorithm here which button to press. And all it's going to do is just keep sampling, checking and checking and checking until it finds the voltage or the analog decimal value that fits between each of these evenly spaced blocks of code. So that's how that works. So let me scroll out of here and I'll just demonstrate that one more time. Code still simulating, fantastic. So again, just oh, I can't scroll in. There you go. So what I'm reading on the screen here is A1 is 912, and that is within plus or minus 30% of the block size. So button 1, 2, 3, 4, 5, 6, 7, 8, 9. No, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that must be. Oh, I can't remember that. Trust me to pick an odd number. Let's pick the halfway point. Yeah, 499. So you would expect 499 divided by 10. 10, that should be 500 or 512. And it's plus or minus 30% of that. So it's within the block of plus or minus for that. I can't remember how I came up with these values. I think I just measured them. Anyway, so that's effectively how this works. Okay, now let me if you wire yours differently, yes, you're going to have to change this little algorithm here. Just be mindful about how you wire this and run a little piece of test code and actually see what values you are receiving. And if you're going to implement something like this, just get your baseline values. You see they're 101, 100, 201. They're close enough to about 100 a piece. 599, 699, 700. Yeah, I think it's a rounding thing. Yeah. If you're going to implement this, try and keep them. All of these resistors have to be even. They have to be the same value, otherwise it won't be linear. When you write your code or you want to modify this, just think about it logically. You want to know if what you're reading is between an upper and a lower threshold, and you know your upper and lower threshold is going to be an even split of all of these. So you just basically take the range and take a little bit off it, and then do like a double ampersand. So if it's between that lower range and this upper range, that's what this means, and then return whatever the current I value is. And you can use that to directly set the joystick dot set button, and then you can put this code in here and then whatever the value happens to be. Okay, so a potentiometer is exactly the same piece of code-ish, but what I've done here is I haven't actually incorporated thresholds. Or have I? What have I done? Threshold 10. Oh, okay, I did. All right, so analog A, right? So this is analog port A. We have a potentiometer, and if I just adjust this, you'll see the buttons are counting all the way up. Now, the difference between this piece of code and the other piece of code is in analog A, analog button read pot, we still call what pin to go read. We still ask for a number of buttons from it, except this time we're not. I'm not implementing particularly a block range. So we read the pin, we get the value first. So this is what this value is here. That's 450. Okay. We give ourselves an arbitrary threshold, but because we don't need to check an upper and a lower threshold, we are just literally stepping up. A potentiometer starts from 0 and goes to 5 volts or to maximum. Since we are starting at 0, so we start our I at 0, we just keep incrementing and just check to see if it's below a certain threshold. And once it exceeds that, so while the analog pin value is greater than I times a range, which is going to be 1024 divided by the number of inputs. So if that's 10 inputs, that's again 102. plus a threshold. Okay, so this is going to be blocks of 102. 0 times 102 is 0. 1 times 102 is 102. 2 times 102 is 204, and so on and so forth. And what it does is it just keeps incrementing I. So this just keeps counting up. Once it gets to a value where the analog is higher than a certain value, this will count up to 13. Count up to 1 higher than what the input range is, and then it will fail and return the last I value. Yeah, so this will step through doing 1, 2, 3, 4, 5, 6, 7, 8, all the way up to the number of inputs you've asked for, because we created block sizes equivalent to an even block. Oh, that's right, the threshold. The reason I added this threshold is when you get to 1023 and you actually get to 1023, actually, why have I got 1024 there? Oh, because it's 124 steps. When you get to 1023 and you match 1023, you never get that last button. So we actually set the threshold 1 block higher, so it at least does one more check. And by that threshold, I made it just small enough to overflow so that you'll still get to that very last button. So that's what that does. What am I doing here? I'm actually saying I'm asking for, that's right, here we go. So I'm reading a potentiometer, and you see how I'm reading for 12 buttons. Okay, if I go and stop the simulation and I say I want, go away, come back code, come back. I want, say, only 5 buttons there. Let's start a simulation. Here it comes. Boop, 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 boop. Why is that still counting all the way up? Why is that still counting all the way up? That's because I changed the wrong one. Stop. I want 10 there, and I'm going to put 5. And see, I knew I did this back to front. Okay, we are going to ask the pot, there's the pot, for 5 buttons and 5 buttons only. And this is the difference. All the way up to 5. It is only going to give me 5 buttons. 1, 2, 3, 4, 5. All the way down to 0. So I can actually scale an analog input to as many buttons as I want. Let's call it, I don't know, 50 buttons. Sub simulations. I want 50 buttons for this one. Start a simulation again. And there you go. It's giving me 52 for some reason. That'll be because my threshold, I think, is set too high. And the chunks are really small. That's exactly what that is. Let me set that back to 0, that threshold. All the way up. Button output. Goes to 52. What am I doing there? I think that's a rounding error, in all fairness. I think that's a rounding error because this is an integer, and when you divide 1024, it's going to give you, and the higher the number of buttons you want, the smaller the blocks are going to be, so the more error you introduce with roundups when you convert an analog, what's effectively a float value, into an integer range. But yeah. All right, well, I will stop that, go back to my 12 buttons. Now, this piece of code works quite well if you are doing a, say, 12 position resistor ladder. So if you got one of those 12 position switches, this would probably be quite, this thing here would be quite sufficient for your needs. So this is just going to keep stepping through, and it's always going to return whatever the last block it was in. Yeah, you see how it overflows? Gives me that one extra, that button 13, when I only actually asked for 12. So you'll just have to play with a little threshold here, just to probably have to just factor in something like that. Start simulation. I think it's just a rounding error. I think I worked out 10 was the way to go. Yeah. Anyway, look, it's a fairly tiny piece of code. It's much better than a lot of if this, if then, that, and else's, and so on. Super quick. This piece of code here does all the work. It's just calculating through And the clever part is just using I as a multiple of the block size. The trick comes in making sure your block sizes don't introduce rounding errors, and it's something you can tune in your code as well. And again, this piece of code will return an integer. This I value is going to be a button number. It's going to be this B0 here, and it's going to return 0 to 12. Okay, so you can use that in your HID code to do something a bit tricky. So yeah, you can use that to reference to the button you want to then set and then release, and so on and so forth. Anyway, that's how I do it in my code. It's you can play with something like this, and you might even come up with slightly different variations because you want a little bit more buffer zone between your zones, or you might want to so you might want to do something in here. You might want to actually set those buttons and then return back. You may not want to actually just use this as a local as a return function. So, but anyway, I hope that clears up how I would do it, and maybe give you some ideas about how you might want to do it. So, you can write this code a million different ways, and I found this was clean and reusable for the most part, reusable. And you're welcome to have a play with it. Okie dokie. Cheers and thanks very much.